Oke, Assalamualaikum warahmatullahi wabarakatuh. The Honorable Professor Dr. Rui Andong from National Tsinghua University, Taiwan. The speaker for today, also Dr. Suresa Gadevan from Nanotechnology and Catalysis Research Center, University Malaya, Malaysia. The Honorable Dr. Nur Fitri, the head of Research Center, Directorate of Research and Community Service, Universitas Islam Indonesia. And very good morning to all the participants, ladies and gentlemen. It is our pleasure to have you in this online webinar, which is presented by Chemistry Department, Universitas Islam Indonesia. Before we start the agenda, it is kindly requested to all participants to to rename the Zoom account with your name underscores institution for us to easier to catch your identity during the event. And the second, it is also kindly requested to switch off your microphone during the session unless the moderator or the host welcoming you to ask the question by direct speaking. And the third, as you can replace your virtual background, please use the virtual background of this event so we can have nice photos for our documentation. So we can start this event. Ladies and gentlemen, currently nanotechnology is very responsible for the unprecedented positive impact in many fields. And there are some research development related with the nanomaterial and also material-based nanosystem has been engineered with some interest for the energy and environmental application. And the development in this kind of nanomaterial, analytical technique, modeling, and optimization, such as the specific application are fast in progress. In another side, the sustainable technology with green chemistry approach is also considered. So in this context, this webinar is planned with main focus for discussing the recent advance in material research for energy and environmental application. And this event is actually conducted as the part of world-class professor program funded by Ministry of Education 2020, as well as from the Global Engagement Grant under the International Office of Universitas Islam Indonesia 2020. So the Chemistry Department, Universitas Islam Indonesia, welcoming you to participate to this event. And thank you very much to the speaker who is accept our invitation for today, and also for all participants for the participation. So we will have the rundown for the agenda for today. The first is the opening. For the opening, we will have the welcoming remark from the head of Research Center, Ministry of, the head of Research Center, Directorate of Research and Community Service, Universitas Islam Indonesia, Dr. Nur Fitri. And then after that, we will have two speech from Professor Rui Andong and also from Dr. Suresa Gadevan. So we will entering the first agenda, which is the welcoming remark from the head of Research Center. For Dr. Nur Fitri, screen is yours, please.
Thank you very much, Professor Fatima. Bismillahirrahmanirrahim. In the name of Allah, the most gracious, the most merciful. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Alhamdulillahirabbil alamin wassalatu wassalamu ala asrafil anbiya wa mursalin wa ala alihi wa sahbihi ajmain. The Honorable our speaker, Professor Wei Andong from National Tsinghua University, Taiwan. The Honorable Dr. Suresh Sagadevan from Nanocatalysis Center, University of Malaya. The Honorable Professor Dr. Fatima from Chemistry Department, Universitas Islam Indonesia as the host today. And Honorable all of the participants in this webinar on materials for energy and environment. Firstly, I would like to express my great appreciation to Professor Fatima and teams from Chemistry Department, Universitas Islam Indonesia, Yogyakarta, for having organized this webinar with the theme Materials for Energy and Environment. This event is supported by world-class professor program from Ministry of Education Indonesia and Global Engagement Grant from International Office Universitas Islam Indonesia. I noticed that the theme of this event has its relevance with the global challenges of climate and energy in the world. The global challenges of climate and energy require new technologies for renewable energy sources, methods of energy storage, efficiency energy use, techniques for carbon capture and storage, climate engineering, as well as an appreciation of the impact of this on the environment. Therefore, knowledge and skills in material for energy and environment are important in order to participate in the emerging challenges to meet climate change targets and the human need of energy. So, on behalf of the Universitas Islam Indonesia and the webinar committee, I thank you for joining this webinar and hope every participant will enjoy this webinar. Thank you.
Okay, thank you very much, Dr. Nur Fitri, for very nice opening remark. So before we start the speech from Professor Rui Andong, it is kindly requested to all participants to switch your video on. We will get the screenshot for the all participants for our documentation. Please, in 3 minutes, please switch on your video on so the admin can catch the photos of all of you. And give your best smile in 3 minutes, please. Admin, please take the capture of the picture. Okay, enough? Admin, is it enough?
Enough, Professor.
Okay, okay, thank you very much. Okay, the next is the main agenda, and for your information that the registered participant for this event is 780 participants for today. But in case that your Zoom meeting getting trouble, so you can also follow the agenda on YouTube. The YouTube channel is Jurusan Kimia FMIPA UII. Okay, so we'll have the speech from Prof. Rui Andong with the moderator, Mr. Ganjar Fadilah. For Mr. Ganjar Fadilah, please, the screen is yours.
Okay, thank you, Professor Isfatima, for this opportunity. Good morning, dear all participants. Assalamualaikum warahmatullahi wabarakatuh. Okay, my name is Ganjar Fadilah, and in this section, I will be serving you as moderator. And as I mentioned earlier from the Professor Isfatima, the nanomaterial or material-based nanotechnology is one of the interesting topics. And it has been widely used for several applications, especially for energy and environment. So in the webinar series, we will focusly discuss in the recent trends of material, especially for energy and environment. Okay, they're all participants. In the section, we have two keynote speakers who are the Professor Rui Andong from National Tsinghua University, and the second speaker is Dr. Suresh Sagadeva from University of Malaya. And I remind you to all participants, please turn off your speakers, and or maybe you can mute your speaker. And for all participants which have a question, you can directly write on the chat column in the bottom of the Zoom. And in the section, I will read and transfer all questions to our keynote speaker. Okay. The first section we have first speaker, that is the Professor Rui Andong. But before we start the section, I would like to read the curriculum vitae from the Professor Rui Andong. Professor Rui Andong is the chair professor in the Department of Biomedical Engineering and Environmental Sciences in National Tsinghua University, Taiwan, and his research expertise in the electrochemistry, environmental remediation, sensor and biosensor, and environmental nanotechnology. And the professor has received the doctoral degree from the National Taiwan University in Graduate Institute of Environmental Engineering. And the Professor Andong also have received more honor and awards, like from Outstanding Research Award from the Ministry of Science and Technology Taiwan, and also the International Honorable Member Award from American Academy of Environmental Engineer and Scientists. Okay, and also the Professor Andong also has published more than 150 papers in international reputable journals. Okay, I think it's enough for me because our time is limited. I will invite the Professor Rui Andong. Hello, Professor.
Yeah, I'm here. Okay.
Yeah, okay, Professor. Okay, I think maybe you can deliver your presentation in 60 minutes until quarter past 10 in Jakarta time. Maybe you can.
Okay, no problem.
Okay, and after that we will continue in Q&A section, Professor.
Yeah. Okay. Thank you. First of all, I would like us to thank Chair Fatima and our moderators, Fadilah, and also would like us to thank the invitation from UII. And it is my great pleasure just to give a talk here. So that's now I need just to share. Okay, so So I believe that now everybody can see my topic. Today, I would like us to mention is that the recent advances in material research is for energy and environment. Since this is quite a big topic, so I would like us to focus the talk on carbon-based nanomaterial. Although the moderators has introduced my background, but here also would like us just to introduce myself a little bit. At this moment, I'm the chairperson at Tsinghua University, also serve as the deans of the Tsinghua International College. This college, actually, we have the different kind of mission. We would like us to recruit the senior high school students to Tsinghua. So that's we would like us to incubate the name from the bachelor degree and names to PhD. So hope that they can learn the more solid the background as well as the advanced knowledge. And at this moment, I also the directors of the Center for Energy and Environmental Research at Tsinghua University, also the conveners of the programs of environmental engineering, Ministry of Science and Technology. This is the government's unit. So that's the now it means that I was in charge of all the environmental engineering programs in Taiwan. At this moment, I also visiting adjunct professor of Universitas Erlangga in Surabaya. Also the visiting professors of the University of Shizuoka in Japan. So get some honors. I think I don't need this to talk about names. I also get some honors and awards that like the chairperson mentions that okay from the 2000s to 2018 they get some domestics as well as some international awards. Okay, and also at this moment, have published more than 200 papers. So from the statistic data, from the Web of Science, my H index is around 49. Per papers has been cited 27 times. Highly cited papers has 3. But when we check is from Google Scholar database, my H index is around 56. I10 is around 139. So that is the background to let you know. Definitely is that the most important is that the research interest here. Like I mentioned, is that the topics today is that the environment and energy. So that's here would like us to introduce you. That's my background. The first is that the environmental nanotechnology. So we'll focus on the remediation or even bioremediation of contaminants in water and wastewater. And we also do some advanced oxidation process, ALP, mainly for photocatalysis. And also would like us to do some to link with energy and names to talk about the capacitive deionization. Also would like us to introduce some material, especially for carbon-based nanomaterial. This is also the main topics that today. I also cooperate with some friends that in nanomaterials in Indonesia or in Malaysia. We are talking about the polymers. So tries to use the polymers for energy application. And for those energy application, many focus on supercapacitor and lithium-ion battery. These two actually now is quite important because for those vehicle cars, also for some other purposes. So the energy storage devices at this moment is very important, and my backgrounds and my research interests will focus on this part. We also do some environmental analytical chemistry, very similar to the deans of your college. So the main skills of my research interest in is here. So here we focus on some photocatalysis and for electrocatalysis. So that's we call this one is the photoelectrocatalysis, means that PEC. PEC can do a lot of things, especially for water energy methods. So going back to our topic, why we want to talk about the energy and environment, because we can talk about the food, water, and energy methods, or even only focus on energy and water methods. All these three topics actually is very important worldwide, especially from the UNDP. From UNDP, you will see that in 2016, they launched 17 goals. We call it 17 SDG goals. From these 17 SDG goals, you always will see that the goal 6 and goal 7 is the waters, clean water. Goal 7 is affordable and clean energy. So it means that the environment and energy will become a top issue worldwide during the next 10 years. Because for SDG, till the 2030, the UN hopes that every country can reach these 17 goals. So that's why now, no matter in Asian country or in European country, people are working so hard to fulfill these 17s. So that's here, you always will see that's the clean energy and affordable clean and waters are the indicators. And this is very important because in Southeast and the South Asian country, we are shortage of energy. We also shortage of clean water. So that's we need to develop very good key technology for environmental sustainability, especially to create clean waters and clean energy here. So the water shortage now is the worldwide problem. So that's here you always will see that when you talk about the water resources in the world, we just think about the whole water resources in the world is just 1 liter. And names in this 1 liter of the water, 97.5% will be in sea waters. And those frozen fresh waters will be around the 2.5%. So 96.5 plus 2.5 equals to 100. And how about the lost available water? Actually, those available water will very, very less, even though just only that's named 0.01%. So that's I mentioned that if we think about the whole water in the world is 1 liter, and names the water resources that's available to mankind is only 1 drop. It's only 1 drop. So that means that for this 1 drop of water, and then we need to supply this 1 drop of water to more than 7.5 billion population in the world. So the water shortage actually is very important and is also the big issue in the next 10 years. So that's why we talk about how to use the nanotechnologies to clean or to provide the sufficient water. So carbon-based material is one kind of the solution. Why I focus on the carbon-based material? Because carbon material we have been used for more than 4,000 years in the world. From our ancient times, we have used the coal char, and from coal chars to activate the carbon until now to do the nano-based carbon material. All these actually are all the same. They are all carbon. So that has the very good physical and chemical property, especially the electronic conductivity is good. Thermal property is good. Chemical stability is also good. Density is low, and their availability is also wide. This material actually is quite good, so that we can use this for electro material. So that's why when we talk about the energy application, carbon-based material is one of them. In environments, we usually use the activated carbons as the good adsorbents to remove some pollutants and some metal ions. So that's the carbon-based material actually is the very good adsorbents for ion removal, and they also can separate gas, especially carbon dioxide, like a MOF, metal organic framework. And carbon-based material also can use as the support for some good catalysts, for example, platinum and gold. So that's that they can be used as for catalysis application. So all these physical chemical property, you always will see that they can have the very wide variety of application, especially in the field of energy, sensing, biomedical, and environment. So why we want to talk about the carbon, because in addition to their good physical chemical property, they also have the very different morphology from 0 dimension to 3 dimension. So that's the 0 dimensional. The most famous one is carbon-60. Okay, carbon-60 actually is quite well known, and the inventors that has got the Nobel laureates. Yeah. But now we would like us to talk about the carbon dose, graphene quantum dose, because carbon-60 actually is that their water solubility is low. So that's it's very hard for us to be used in environment as well as in energy. But the carbon dose and the graphene quantum dose, they have some functional groups, and water solubility is relatively good compared to carbon-60. So there's the application is relatively wild in comparison with carbon-60. We also have quite a good image for one-dimensional carbon, like the carbon nanotubes from the 1991. And we also have quite the hard issues two-dimensional nanomaterial, like the graphene quantum dots or graphitic carbon nitride here. And a lot of people also focus on three-dimensional. Now the most famous three-dimensional is the metal organics framework. We call it the MOF. No matter talk about MOF or GIF or the covalent bondings, the frameworks that COV, all belongs to this the three-dimensional carbon. Today we will talk about the highly ordered mesoporous carbon, and some will be talk about the carbon sponge. So that's all this. Actually, you will see that there's illustrations for their structures: 0 dimension, 1 dimension, 2 dimensional, and 3 dimensional here. So how to use this carbon? So that's in 2008, one paper published in ENGUA. They talk about the mesoporous carbon. So that's here they emphasize the several application. One is for catalysis. So not just only for catalysis, that they also can serve as the catalyst, the support. They can do the separation, gas separation, water purification, or even for the gas chromatography or liquid chromatography, all are possible. And carbon-based materials, since that they are highly ordered, the mesoporous, so that's that they have the photonics behavior and can serve as the photonics materials here. And they also can do the energy conversion and energy storage because that they have quite a good electrochemical property. So according to those, there's a good physical chemical property and there's wide availabilities. So that's we would like to talk about the carbon here. Since carbon contains a lot of, so that's today the talk will mainly focus on the graphene family. Graphene family including the graphene oxide, reduced graphene oxide, or even for graphene quantum dots. That's the 0 dimensional graphene family. Has very unique optical and electrochemical property. Yeah, so but for energy and environmental application, we mainly focus on the graphene oxide, reduced graphene oxide, and graphene quantum dots. This especially for the reduced graphene oxide and GQD, because that these two material actually they have the very good electrochemical property, conductivity, and names that they can dissolve in the water. They have the very limited functional groups, so that will be good. So for electrochemical properties, names that can be used for lithium-ion battery, solar energy, supercapacitor, even for sensing or for catalysis. For optical property, they can be used for sensing and for environmental applications here. So here give you some ideas about this graphene family, even though it is quite popular. Okay, from your left-hand side here, you can see this one is the graphene. They have the no functional groups on the surface. So that's their conductivity is good. So that's you can see that's their electromobility is quite high. But this material cannot be dissolved in waters. They only can dissolve in solvent. It is not as easy to use in our daily life. So that's the people would like us to oxidize them into the graphene oxide. But the problem for graphene oxide is that they have too many functional groups, have a lot of phenolics, hydroxyl and carboxylic group. So that's their electrons mobility is very low. You will see that is quite low here. So that's the people would like us to do it is to use for reduce graphene oxide. So that's they have the very less functional group here. So that's that will be good. So there's conductivity will be good, and names that there's electronics property will be good, and then they can dissolve in water. So sorry, that's this two value actually is inverse. For graphene oxide should be insulators. Names for reduced graphene oxide, their electrons mobility should be around 0.05 to 200. Okay, sorry for the mistake. Yeah. So now we talk about some case here. One is the zero-dimensional graphene quantum dots here. So what we want to do this material, we know that the two-dimensional graphene oxides, they have quite a good conductivity, but their optical property is not good enough. So when you narrow down this two-dimensional graphene oxide or reduced graphene oxide, they have just several layers and named into the very, very tiny parts. So they will become the quantum dots. When we talk about the quantum dots, it means that their particle size will be less than 10 nanometers. Betas will be around 5 nanometer. So when all the particle narrow down to the quantum dots behavior, they have quite a unique optical property. So that's from the graphene-based materials to graphene quantum dots, from two-dimensional to zero-dimension. So their electrochemical property will be there because their property is the graphene family. But when you narrow down to quantum dots, their optical property will be enhanced dramatically. So it means that as the zero-dimensional graphene quantum dots, they have the quite unique physical chemical property, especially for optical and electrochemical properties. So we can use this electrochemical and optical properties to do a lot of things. Yeah. And the other case is the three-dimensional graphene family. So from the two-dimensional, since at the edge, they have some functional groups, hydroxyl functional groups or carboxylic functional groups, so that they can link together. So that we can try to add some metal ion get inside to the names to link it together. So that's the two-dimensional will become three-dimensional. What we want to do those the three-dimensional from the right-hand side here, you always will see that they have the two-dimensional frame here. So they can keep the electrochemical property of reduced graphene oxide or graphene family, but they have a lot of bit space get inside. This bit space actually they can have some electrolyte get inside. If they have the electrolyte here, names their electrochemical property will be enhanced, especially when they serve as the electromaterials for lithium-ion battery or for supercapacitor. So that's the for three-dimensional graphene family. A lot of people would like us to use them as the very, very novel electromaterial for energy storage and energy conversion. That is the case here. So How to prepare the graphene quantum dots? That's quite simple. You can try to use the top-down methods. That means that when you have your graphene family, reduce graphene oxide, some others, names, you can try to use the physical methods just to grind, to chop them into the quantum dots. That's the physical method from top down. And from the bottom up, you can try to use the chemicals to do. For me, I prefer to use the chemical method. The chemical method, actually, we can fabricate quite a nice and quite uniform the particle size. Okay, so we can do the pyrolysis of the citric acid or other carbon materials. So that's here is one kind of the citric acid. Citric acid has the 3 carbon, 1, 2, 3. So that's if they have the 2 citric acid names that they can form the benzene-like structure. So that's they are quite easy to form, the 0-dimension graphene quantum dot. So that's we just use the temperature as the 200 degrees C, 25 minutes, and names that they can form. Here you can see that's when you irradiate the UV light at the 360, they can emit the wavelength at around 460. So that's their fluorescence property will be good. And we can do the surface modification so that they can do a lot of optical and electrochemical property. If you do not have the citric acid or the other carbon materials that are on your hand, that will be also quite easy. We can buy some carbon-based raw materials from the market. So that's every country has the agricultural waste, like a passion fruits, like a coconut juice, like apple juice, or the citron. All this actually contains a lot of citric acid and some sugars, glucose and some others. So that's for example, in my lab, I just used the passion fruits and put some boric acid and names that just get rid of the seeds of the passion fruit, have their juice here, and put the boric acid get inside. Still use the microwave 170, 20 minutes, and names we can get the graphene quantum dots. If you ask the boric acid get inside, you can get the boron doped graphene quantum dots. And for those natural products, most of them contains the nitrogen. So that's when you use the natural products that's to fabricate your graphene quantum dots, you always can get the nitrogen doped. Since you have the nitrogen doped, so that's their electron density will enhance dramatically. So that's their quantum efficiency will be good, the names that their electrochemical conductivity will be good. So that's we can use this for the paper strip the sensors to detect the tetracycline or some other, and also we can decompose them. So that is quite simple. So the preparation methods of the graphene quantum dots is quite simple, so that we can use this material for a wide variety of applications. So that from now on, I would like us to introduce you how to use the graphene quantum dots for application in environment and energy. Here is their physical chemical property and their morphology here. From the passion fruits, okay, yet from the natural carbon, we can get the quantum dots here. So that's here is the case. So that's when you see the blue colors, that's the graphene quantum dots. When you use the atomic force microscopes to see the topography and to do the thickness of the lost carbon-based material, here you can see that's their thickness only around 2 nanometers. 1 layer of the carbon is around the 0.334 nanometers. If you ask the graphene oxide will be around 0.8 nanometer. So that's the 2 nanometer means that they only have the few layers of carbon. Since there are only few layers, so that's we can make sure it's a graphene quantum dots and not the carbon dots. On figure C, we'll see their particle size from the TM. So that's their particle size at around the 9 nanometers. Names here is also the case. So that's I don't want to go in detail. So that's for this GQD, you can do the energy application first. So that's since the GQD is the zero dimension. So that's the particle size only for around 5 to 10 nanometer. It is very hard to see and to separate. So most of the time, we will use the zero dimensional graphene quantum dots with some support. And here we select the one natural occurrence the materials as they are supposed. We call this one is halloysite nanotube. Halloysite nanotubes is the naturally occurring layers clay mineral. We can find these materials in soil. So the characteristic of this material actually they contains the aluminum oxide inside on the inner surface, and they have the silicon dioxide on the outer part. And from the soil chemistry, you always will know that since the layers do the balance. So alumina is the 3+, silicon is the 4+. So when they maintain in the same material, so most of the time, your silicons will become negatively charged, and your aluminums will become the positive charged. So this material actually has been widely used to absorb the metal ions in soil. So that's quite common. But now we use this for energy application. Since their outside is the negatively charged, inside is the positive charge. So that's we can try to let the electron get inside. So they can store some energy here. And then we put the graphene quantum dots on the surface. So that's here is the case. I'm sorry. So that's here is the case. When we put the graphene quantum dots on the surface and then tries to do the surface modification, and then we can see this one is the halloysite nanotube. Do the test for surface modification, and then we can get some good absorption abilities on GQD. So that we can put it. If you would like us to recover or enhance their property names, that you can add some metal oxide, for example, like iron oxide or some other. So here is the case. I just very briefly and very quickly to see we still can see a lot of the graphene quantum dots names that this spacing is the 0.21, very close to the carbon. Okay, and their particle size is around 9, very similar to the GQD we fabricate from patient fruits, and then you can see that they have quite a good optical property. And then when we put the test on the surface, the names outside, this outside actually is the test. When we enlarge it, we can see some spot. This one is the graphene quantum dots here, so that we can see the case. So here we always will see their microstructures here, including SPS, XRD, BT surface area, and the thermal property here. I don't want to go detail. If you are interested in that, you can read my paper. We have published this one in 2008. I'm sorry, 2018. Okay, yeah. Names the electrochemical performance here, you will see that they are quite rectangular. It means that the graphene quantum dots plays a very important role here. Names that their behavior is the ideals, EDLC, electric double layers capacitance behavior. And here we also can see the quite a good triangle. So that's you will always will see there's capacitance can be around the 320 farad per gram. Actually, this value is quite high. Named that their cycle numbers can be up to around the 5,000 times, can maintain around 87%. So that will be also quite good. So that's from here. So we also can get this if you have the iron oxide to get inside, the value will increase a little bit because you add some metal oxides, so that their value will be increased a little bit, but may not be good for their energy density and power density. Here is the case for energy density and power density. Here you always will see that when you only have the GQD and HNT, their power density actually will be high, but the energy density only around the 30 to 50 watt-hours per kilogram. When we add the iron oxide, their energy density decreased a little bit from 29 to 10.4. The reason is that we count the energy density and power density by weight. And for HNT and GQD, actually they has quite light. So that's to every kilograms that they can have the more GQD on the surface. So that's their power density is high. Since iron oxide is much heavier than GQD, so that's even though their capacitance is high, but their energy density decreased a little bit. But you always will see that the nanomaterials we ask that the iron oxide inside or not, their value will be good. For this product, we call this one is the Reagan product. Theoretically, my goal is to try to have our power density higher than 100. And our energy density will be higher than 10 or even 100. So that's the main goals in my lab. Actually, we just have the 100 the rules. So that is the case here. But now the power density is quite easy to get 10. Names that the energy density will quite easy to get around 50. So it means that there's not just only for supercapacitor and battery. There's we call this one is the supercapacitive battery. Means that they have the very high power density as well as they also have very good energy density. In the next 10 years, we hope that we can get this Reagan process to this region. Okay, so that's their value can around 100 and 100. In that case, names the material can be used in real industry. That's the case. Not just only for hollow side nanotube, you still can immobilize the GQD on the surface of two-dimensional. For example, VNS here, vanadium dioxide nanosheet. So that's here is the box V2O5. We try to use the hydrothermal methods to separate the box of V2O5 into the layer 1. And then we put the GQDs on the surface of our VNS. So that's what we call it the VNS GQD. Here we do not use the citric acid or some sugar. We use the pyrene. So that's the pyrene will be quite easy to form GQD and their surface will be relatively high. And names we try to fabricate our negative electrode. We use the carbon cross and then put some three-dimensional. We call this one is the mesoporous carbon sphere. You will see their morphology here. So that's the one electrode used is the VNS with graphene oxide. The graphene quantum dots. And names that the other electrode we use is the mesoporous carbon sphere. So we merge them together. So we call this one is the asymmetric supercapacitance. Okay, yeah. So their value will be here. This one actually is the case with the VNS and graphene quantum dots. The upper part here. The lower part is another case. We call this one is the MCS mesoporous carbon sphere. So that we can see the sphere here. And then from the TM, we can see they have some light spot here. This one is their pole here. So that's here we can see the low angle XRD and names that they are quite good. And names from the Raman spectroscopy, we also can see the D and G band here. So that's we use these two together and their electrodes property will be good. Here is the case we have the VNS GQD. The value can be around the 550 Faraday per gram. And if we have the mesoporous carbon names, their value will also around the 550. So from anodes, from anodes, their value will be around the 550. From cathodes, there's a capacitance will around 550. So that it means that this value will be quite close. And then when you merge them together here, when you merge them together, and names that they can have the very good efficiency here. So that's the when you use the MC as the negative electrode here. So that you can see that the potential is negative. When you use the vanadium dioxide with the GQD, names that the weight percentage is 10, they can serve as the anodes. So that you can see that the potential is positive. So that's the behavior will be quite good here. And there's a potential will around from 0 to 1.5. So that's quite a large. So that's in that case, we can get the Reagan plus is here. So that's the, I mentioned that that's our value is 100 and 100, and that is the goal to here. But at this moment, with our value is the larger than 10 and 10. That's the essentials for electrode material. So our value actually is the relatively high compared to the now reported the data here. You always will see their value is here. So it means that when you use the graphene quantum dots with carbon with some other carbon-based material, there's energy and power densities will be relatively high here. So you always will see that there's the retention will be also good after 5,000 cycles. That means that the discharge will be good. Here we analyze the contribution of the diffusion and capacitive. We always will see that when you use the high scan rates, the capacitive contribution will be much higher. Means that the GQD actually play a very important role here. So not just only for energy application, you also can use these materials for capacitive deionization for environmental application. The same ideas is the same. Capacitive deionization actually is the capacitive deionization, their principle is very similar to supercapacitor. They just store electron get inside, and then we just change the electron into those ions, sodium ion and chloride. Yeah. So the principle is the same. So that's here we always will see that we just use the graphene quantum dots with halloysite nanotube. Hope that you remember that we use this material for supercapacitors. Okay, yeah, and here we use the same material but just add one nitrogen dopant here, and names that to use the capacitive deionization. So that's that we just apply some brown waters or gray waters to get inside. They contain some contaminants and ions get inside. When they pass through the cells, and names all the ions will be removed. So that's that they absorb on the surface here, and only water molecules can penetrate. So that's after the treatments here, you always will see that's from the contaminants that contain some impurity here, color is pink, and names becomes the blue, means that's the colors of pure water molecule here, and names we can do it so that we can get the desalinated water here. So the concept is very simple, and all the physical chemical properties will be the same as the data I mentioned, but we use it for removal of ion. Here you always will see when you change the flow rates and the names that the potential and the concentrations of our ion, we can get different kinds of the Reagan plot here. This one is the specific electron capacitance. This one is the specific electron absorption rate. So we call this one is the CTI Reagan plot. This CTI Reagan plot, you always will see that their value is quite good. So that's when you compare our work with some other good good material, like even though for MOF here, for carbon bond, 3-dimensional activated carbon, this material actually is quite good compared to low carbon-based or some advanced material here. So that is quite good here. We published this just in these years, okay, in environmental science nano. And for GQD, they are not just only for energy and environmental application. We still can use this for some other possible application. If you are not in the field of environment and energy, you still can be used for sensing, for analytical chemistry, or for biomedical application, or even for upconversion for photoelectrochemical application. So just to give you some example. We published these ideas in Science Report in 2019. We tried to immobilize the GQD and SGQD on the penny. Penny is one kind of the conductive polymer. So that's what we used aniline as the monomer, and then tries to immobilize into tries to fabricate us into the polyaniline, we call penny. We put the gold on the surface actually, so that you can see the gold here. Names the puts the NSGQD here. So that's the names immobilize these materials on the surface of electro, platinum, and some others. So when we enlarge the names, we can see that this one actually is the penny, okay, quite good, one-dimensional. When you put the gold on the surface and names, you always will see that they have some spot here. This spot is the gold nanoparticle. And names we use this to put the NSGQD and put the anti-CEA antibody and names to detect the CEA. So the biomarker actually is not the good conductive material, but GQD and gold and penny are all good electroactive material. So that's their conductivity will be low. So that's when their conductivity will be low, their impedance, this diameter will be low. When you push the CEA, it's not the good conductive material, so that's their impedance increase dramatically. So that's from the diameters of this impedance, we can get their calibration curve here. So that's that we can get the kind of good calibration curve here, and names we can get the numbers of the CEA. We still can use this carbon dose or graphene quantum dose, the names to detect copper, or use some antibiotics like a CIP. So that's you can see that's when you use the graphene quantum dose to detect the copper, their detection limit will around the 4.8 ppb. This value actually is more sensitive than name AAS, okay, and very close to ICP OES. So that is quite good. And we also can use this to detect the CIP, a kind of use the antibiotics for our food. Okay, so that's you can see, and their sensitivity is also good. So all this actually just that you know that the graphene quantum dots actually can do a lot of things. Oh, okay, forgot to mention, we just published this papers last month. Okay, yeah. Okay, and you also can use this to detect some environmental pollutant like for nitrophenol. So that's that we use the citric acid and some sulfurs salts, mercaptose propionic acid, and then tries to do it. And then we put the gold precursor get inside. Since your GQD is the reducing agent, so that's that they can reduce your gold ion into gold nanoparticle, so that we will get the gold GQD, and then we can use this to decompose nitrophenol as well as to detect nitrophenol. So their efficiency is also quite good. We published this 2 years ago. You also can use the GQDs, names use the name added with beta cyclotetranes to detect the cholesterol. So that's here is the case. You can use a GQT, a name has the beta cyclotetrane, a name there on the surface, a names if you have your ferric cyanide, a names that they can be here. If you have the cholesterol, they can get inside your cyclotetrane, and names that replace the ferric cyanide. So that's the peaks, the electrochemical properties will enhance dramatically. So that's from this electrochemical properties, we can detect the cholesterol quite easy. You also can use it for upconversion. Upconversion is quite new at this moment. We always know that the graphene quantum dots that they can do the down convergence. The optical property means that we use the low wavelength 360 names that they can emit the 440 or 460 nanometer. So that will be the case people would like to use. But the one characteristics of GQD is that they have the upconvergence property. So that's when you use the long wavelengths like 730 names, they still can emit the wavelengths at around the 440 nanometer. What's the advantage for them? Just think about that we have the solar energy. For those the solar energy, people would like us to use the visible light even though for IR region, so that they can enhance their light penetration and the light harvest efficiency. But it seems quite hard for us at this moment to use the long visible light near IR range. So if you add the upconvergent GQT get inside, names they can use the long visible light 730 or even to 900 nanometers. So that's they can recover the low light and names that your solar energy become more efficient. So that is the case. We try to develop the lowest upconverging case. So that's for GQT. They are not just only to receive the UV light, they also can receive the long visible light, so that they can do the same way simultaneously. So that is the good way. So that's the principle is here. Okay, yeah, but since time is very limited, I don't want to go in detail because I just finished a half, so that I need to finish as soon as possible. So that's the names that we can also use the two-dimensional reduced graphene oxide for energy and environmental application. So this one actually is the case for graphene in reduced graphene oxide. So that we can see the sheet here. The surface areas is here around the 44 and the name 570 is relatively high. We immobilize some metals on the surface of reduced graphene oxide and names, you can see that they can surface very good. So when we use this one, this covers image to tell you that when you have some contaminated water, you can see that the color is brown. Okay, the color is brown. When they pass through the reduced graphene oxide, immobilize some metallics, some metals, the color will be clean. Okay, so the case is quite simple. We just use the boron topes, the reduced graphene oxide, and then put the iron nickel, and then they will reduce this to the zero valence, the iron and nickel. So that's here is the case here. So we use this to decompose the trichloroethylene, some chlorinated compound. So that's just only around 20 minutes. All the chlorinated compounds can be decomposed, and names that they will convert into ethane. So that will be good for them. Yeah. So here is the case when we use the reduced graphene oxide or boron topes, the reduced graphene oxide. The case will be here, and we also can use this to remove some metal ion like coppers here. So that will be the case here. We can do We also can use this materials for CDI, like I mentioned. If you put the MnO2 on the surface of the nitrogen doped RGO names, you can see that they can remove the NaCl. They also can remove some pollutant like microcystine and some coppers here. So all the case is possible. You also can try to use some metal oxide get inside names to do the CDI here. Okay, graphite names to remove to merge with our MVO here. Names use the hydrothermal methods and names to coat it on the surface of titanium plate. And name there forms our materials for CDI. So that's from these ways, you always will see that they can try to remove some ion, especially for high concentration of NaCl, and names that they can get the clean water. Okay, so the final part I would like us to introduce is the three-dimensional highly odorous mesoporous carbon. Here is the case we can try to do highly odorous mesoporous carbons. Originally, there's the similar to this one, like a sugar. But when you do the carbonization, they'll become here. So that's here you can see that we can see the black colors. The black color is carbon. We can see the white color, quite the good highly odorous. Okay, this one is their whole. So that when you get enlarged name, use the high resolution TM, we can see that their strict is here, a name get inside from the high resolution TM. We can see their pole here. So that's you can see that the arrangements of the pole is quite homogeneous. Yeah. Okay, so that we call this one is the highly ordered. You can put any kinds of the metal oxide get inside, TiO2, GnO2, and GnO, and some others. So that we always can see here. So that we use this for lithium battery. So we have the highly ordered here, but they have the pole. So that the lithium can store in their pole. So that's when you store the discharge, the lithium ions will be get inside and then get outside here. So that's that they can get inside the TiO2 here, or get inside the carbon. We can put the MnO2 get inside here, and names that you always will see here. Use the EDS mapping, use the highly ordered mesoporous with MnO2. Then when we add the 5.4 weight% of MnO2, their case is here. 8.9 is here. 12.8 weight% of MnO2 is here. You always will see that carbon, oxygen, and mechanisms are all the same. Means that our MnO2 is the homogeneous get inside into the OMC. So we can get quite a good electrochemical property, and names also can be used to remove the dye. So that's the name we can recover the loss at highly ordered mesoporous carbon here. So that's here is we put just 100 milligrams of the methylene group. So that's that they can remove in 2 hours. So that's the efficiency quite good. You can see that the absorbed amount is almost 100 milligram per liter, means that that's all can be removed. We can use this one for lithium batteries. I don't like to introduce this in detail, but you always will see that their value will be good. So that you can see it when we use the asymmetric one, there's potential window can be around 2.2. So that's their value will be high. So just remember, I mentioned that our goal is here, 100 and 100 to this region, but now you can try to see that's the 10 to 10, okay? 10 to 10 can publish your result in a very good journal. If you can guess 100 to 100, maybe you can publish your papers in GWAS, in Science and Natures. Yeah, okay, yeah. So we also try to use the mesoporous carbon spheres. We mentioned it previously, so that's I would like us to do it very quickly. So we put the tin oxide on the surface. Okay, so that's outside actually here is the tin oxide, the black one. So that's you can see that when you use the line profile, this one actually is the carbon. This one actually is the tin. So that's the inside. There's the no tin get inside, but outside we can see that they have the high concentration of the tin. So that it means that the tin is just go outside. We use this for low good lithium batteries as application. So that's our value is here. So that's you always will see that's the much higher names the reported data. We also use the three-dimensional for CTI. This one is their morphology here. Their pole is high. Okay, so that's their pole is high. So that's the penetration will be good. So the SEM image here, you can see that we have another pole get inside. So that's the water penetration, electrolyte penetration will be good. And names that there was high surface area, so that's ion as well as electron can be absorbed or removed very, very fast. So that's what we use this for three-dimensional RGO, only for three-dimensional RGO compared to some other activated carbon, CNT and some others. You will see that's their value will be relatively high. So finally, I would like to use around 2 minutes to introduce the agricultural waste that derive the three-dimensional carbon. This one actually is very important because those agricultural waste actually is quite abundant in Asian countries, so that we can get a lot of different kinds of agriculture from different countries, and this is the cost benefit. And most important is that that's the use of this agricultural waste to fabricate three-dimensional carbon is the world trend, especially for circular economy. That also one kind of the very important principle for SDG. Okay, yeah. So that's the we can try to use the, for example, the corn leaf, okay, coffee bean grounds, or use the sugarcane bagasse, names we can grind, names that to fabricate very simply to form the carbon, names to form the supercapacitor or the CTI or some biochar. So that's what we just use this very simply grind and name carbonization for 54 hours activate to do the activation at around the 700 to 900, and the names we can get the very good way. So that's the here you always will see they will have the some residue here. They are from coke. This one may not be good, but their surface area will be high. So that when we use the coffee bean, yeah, so the activity is the temperature is the 850, and then the surface area will be around 3000. That's very, very high, very, very high. And names that there's electrochemical property will be good. So that's the here you always will see. We can up to around 100, but unfortunately that there's only around the 30. So that's our goal is tries to move these ones to here, so that's that they can around the 100 and 100. So that's our goal. You also can use the coconut shells to do it, and for CTI, we just published this in desalination this year. And you also can use the sugarcane bagasse as the scaffolds to immobilize the highly odorous mesoporous carbon. So all these actually are possible. All these are possible. So that is the case. So finally, I would like us to introduce some idea. Here we do not talk about the conclusion, because for nanotechnology we do not have conclusion. We only have the opportunity. The opportunity is that we can try to fabricate the multifunctional composite and use the carbon as the support. So that you can try to fabricate the various materials on graphene or some carbon-based materials to induce more function. You can immobilize with molecule, biomolecule, or so nanoscale objects or polymers. And names you can try to do the water energy methods. Here you can put the porous carbon here and name immobilize your metal oxide. Here is one carton here you can see. If you have the highly porous carbon here, They can do the capacitive ionization, supercapacitor lithium battery for energy. You have the metal. Metal can do the reduction part. You have the metal oxide like a TiO2. You can do the ALP oxidation part. And then you can merge all the function, no matters in chemistry, in environments, in biomedical, as well as in energy together. Do the energy CTI reduction oxidation together, and then you can apply no matter for water treatment technology for energy. That will be good. Okay, so that's the talks of my today. Thank you, and also would like us to thank my library students and the financial support from the most of Taiwan. Thank you.
Okay, thank you, Professor Rui and Dong. I think that is, thank you very much for transferring the interesting topic for us. And we have collected some questions, and we have 3 questions, Professor. Okay, wait, yeah. I will share some screen for you. Okay. This question, Professor, from Dr. Tatang from UIA, Universitas Islam Indonesia. Okay. And okay, maybe she asks from Dr. Tatang currently doing research related to enzyme immobilization using several immobilizing, and can the carbon nanotube material be used as enzyme immobilization agent, Professor?
Okay, so that's the answer is yes, you can use the CNT or the other one-dimensional materials to do, but for those enzymes, you only can immobilize on the surface. But for CNT, you need to realize that the CNT surface actually that they are not have the good functional groups. So try this to do the surface modification first. Try this to let them have some oxygen containing functional group, or tries to use the surface modification. For example, you can use the EDS and HS chemistry to immobilize the EDS and HS to let them have the amine group. And then if they have the amine groups of the carboxylic groups, the names that they're quite easy to immobilize your enzyme. Okay, that's the suggestion. Okay, yeah, but the answer is yes.
Okay, Dr. Tatang, if you have any question, maybe you can use the raise hand application.
Clear enough. Thank you, Prof.
Okay, clear enough. Okay.
Okay, and I also see some comments from the conversation window. I will reply is this when I finish my talk, and names tries to finish all the comments to you. Okay. Yeah.
Yes, thank you.
Okay, thank you, Professor. Okay, maybe
okay, you're welcome.
Next question, Professor. From Hendra Taufik. How can we create into nano size? Are there any special tools to make it, Professor?
Okay. For the preparation of the nano size of the material is quite simple. We have 2 kinds of the method. One is for top-down. Means that we use the physical methods. So if you have your box material like TiO2, you can try to use the high. You can use the thermal methods to burn it and then to condensate. That's one case. Second is that you use the ball mining. Okay, so that's if you have that's the name. Ball mill. So that's you can use balls to grind the names into the small one. That's the physical method. But for me, I would like us to use the chemistry. We use the low material, and the name use the some capping agent tries to the names to become the nano size. The method actually now is quite well established. People, you can find the methods from papers. And the third one, how to isolate hollow side. Actually, the hollow side nanotube we use was both from company. I have no idea how to isolate hollow side the nanotubes from soil. I'm sorry, but in Taiwan we're quite easy to buy hollow side nanotube, and the price is very low. Okay, yeah.
Okay. Hello, Mr. Hendra Taufik. Maybe do you understand for the detailed answer?
I think for Mr. Hendra Taufik, maybe next talks will let you know how to prepare the nano size, because Professor Sudhatevans, that they will talk about the fundamental of the nano materials. So that's, I believe he will mention how to prepare the nano size, the nano material, and there's the physical chemical, their fundamental physical chemical properties. Yeah. Okay.
Okay. Okay. I think we don't have feedback from Mr. Hendra Taufik. So the next question from Mr. Yudhistira from IPB. Professor, can you tell us how to isolate hollow seed nanotube from soil, Professor?
Okay, yeah, we did not isolate hollow side nanotube from soil. We bought the hollow side nanotubes from company, and the price is very low. So that is the case. Yeah. So at this moment, I have no ideas how to isolate the hollow side nanotube from soil, but I believe that that's the we can find, because the discovery of hollow side nanotubes, I think it was in 1970s. That's quite a long time ago. So that's the people would like us to use this for their application at this moment. People at this moment that they do not to isolate them by themselves. Yeah, yeah, they buy it. Okay, yeah.
As information, Prof. Rui, because in Indonesia there are some halloisides deposit also in nature, but I think that it is a different form between the hallousite and also hallousite. Yes, hello. Yeah.
Yeah. So
yeah.
The case, if we would like us to isolate, maybe we need us to go back to the original papers to see how to isolate. We can try to find if you have interest in that. But since in Taiwan that the price, the hallousite nanotube and some others clay are quite well established, and then we all can buy. So that's the we do not to isolate it. Yeah. Okay. But I believe that we can find some reference to see how to isolate. Yeah.
Okay. So we have received many questions, Professor, and we
yeah. So that's
minutes.
No worries. I will respond.
Okay.
Item by item.
Maybe
okay.
Maybe you can answer the question. Right.
If if they okay. Yeah.
From Fitriani from Aceh. How can you rate ferrocene into inner side of beta CD, Professor?
Oh, the size of the CD is quite big. That's around the 0.3 to 0.4 nanometers. But the ferrocene actually is quite small. So that's during the preparation, they can do we call it the host gas inclusion chemistry. So that's that they can get inside, because that they have some interaction inside. Yeah. So that's quite easy. You just prepare and follows the papers names. You can get it. Yeah. Names that they can get inside, that not the outside. Yeah. Okay. Even though their inner and outer size of the beta tetracycline are different, but for ferrocenes, they can get inside, no problem. Yeah. Okay. Yeah.
Okay. Ms. Fitriani, maybe do you have feedback for Professor?
I think it's okay.
Okay, it's enough. Okay.
especially if we use hydrothermal carbon.
Okay, maybe.
They have those two kinds. If you would like us to the waste, the agricultural waste, that's quite simple, because for agricultural waste, you just use the NaOH to do the pretreatment. And NaOH actually they can create a lot of gas, and they also can oxidize some carbon. So that's the when they oxidize some carbon and produce gas, names that they will produce coal get inside. So that's the when you do the carbonization, some organics will be also decomposed. So that's the they will decompose inside. So they also can get some pole. So that's the for those mesopole and the micropole for agriculture. If you just add an NaOH mix up and then use the high temperature, they will produce the pole there. If you would like us to use the low materials to fabricate the mesoporous carbon, you need this to have the pole forming. We call this one is pole forming in material. They are formed, for example, you can use the surfactant from the micelle, and then from the micelle, you can cause some material on the surface. So that's that they can link together, and names that the pole will be there. During the carbonization, your polymers outside the micelle will become carbon, and names that they will form the pole get inside. This method actually is also quite well established in 1990s. So if you have interest in, I can send you some papers and the names you will know. Yeah. Okay. Yeah.
Okay. I think it's enough, Professor, because our time is limited. So thank you very much for your sharing your experiences. I hope this material will give more beneficial for us. Okay, thank you very much, Professor.
Thank you, and I will try to respond to all the comment. Okay, thank you. Okay.
Yeah. Okay, dear all participants, I'm sorry that the Professor Roy Endong cannot answer all questions. Maybe the next time. Okay. So the next agenda is section 2, and in the section 2, we have a speaker that is the Dr. Suresh Sagadeva from University of Malaya, Malaysia. Maybe hello, Dr. Suresh.
Hello.
Yeah, hello.
Yes.
Can you hear me, Dr. Suresh? Okay. Hello, Dr. Suresh. Maybe.
Yeah.
Okay.
Yeah.
Okay. Maybe you can start your presentation in.
Yes, I shared.
Okay. In 60 minutes until 11:30, Dr. Suresh.
Hello.
Hello.
Yeah. Okay, please.
I shared my.
Yeah.
Once again. Sharing now.
Yeah, you can start now. Hello, Dr. Suresh.
Yes.
Okay, you can start now, Dr. Suresh.
I didn't say my PPT. Where is that?
Okay, maybe you can deliver in 60 minutes.
Okay. Where is my PPT? It is shared.
I can see.
Yes, we can see, but please maybe you
Yeah.
use a slideshow, please. Yes.
Now it's okay?
Yes, okay, okay.
So can I start now?
Yes, you can start now.
Yes, sure, please.
Okay. First, I would like to thank Professor Fatima giving the opportunity to talk about on recent advances in nanomaterials, fundamentals, property, and application. Before start my lecture, I would like to say something about our center, Nanotechnology and Catalysis Center. You can see here, this is the University of Malaysia. It's located in the capital city of Malaysia, Kuala Lumpur. This is a IPS building located inside the university campus. Our center is located in the third floor. Nanotechnology and Catalysis Research Center uh, has been established since 2001 at University of Malaya as a specialized center of excellence in nanomaterial and catalysis. Almost 2 decades, we are doing research on different research topics: energy catalysis, biomass catalysis, environmental catalysis, and chemical catalysis. Our center vision to be an internationally renowned and recognized center of excellence in catalysis and nanomaterials. You can see here, we are doing research on the different topic of material design, smart materials, chemical catalysis, energy catalysis, and also environmental catalysis. Our center offers the student, researchers, and academicians as a wonderful place to study and research. Our center is highly interdisciplinary in that we are working together like chemists, biologists, physicists, and engineers all work together to develop amazing the new material with remarkable properties. You can see here, I mentioned here the catalysis and nanomaterial design. We are doing research on nanocatalyst, nanomagnetic materials, nanocarbon, nanosemiconductor oxide, nanocellulose, G-carbon nitride. Like this, we are working on that smart nano material. Those who are interested to collaborate with us, you can send an email. We can do joint research activities and as well as joint research proposal also. You can see here, these are all our research areas. If you want to check if any more information, you can see our center website. You can get more and more information. In addition to that, we have the sophisticated facilities in our center. You can see here that Raman, VSM, wall effect, FSM with EDAX and X-ray diffraction. So we provided sophisticated facilities in our center, and also we can provide the technical support for the material characterization. You can see we have very good reactors and as well as very good material characterization of instrument, HAR, Z potential, XRD, PSC. So you can see our website. We provided technical service promotion. This time we offered the 20% for more than 5 samples. If you need any characterization facilities, you can make use of this opportunity. You can contact through this email ID. This is the contact number. So we offered material characterization facilities in our center. Every month, you can check that our university, our center website. You can get more and more information. Now I'm going to start my lecture, recent advances in nanomaterials, fundamental properties, and application. You can see this slide is very quite interesting. How the scales are different: macro scale and micro scale and nano scale. So 50 years before we used in that macro scale. You can see this is a visible state. The normal human eyes we can see. Okay, we lived in that macro world. After technology development, you can see the 1950 to 1970, we lived in that macro scale. After the optical microscope is developed, some products made by the microstructure material. So we can see with the help of optical microscope, 1970 to 99, microelectronic devices played a vital role. After that, we can reduce the size in the nanoscale. Now we can, the nano technologies played a vital role in the 2010 to till now. We are, many products made up of nanostructure material. Like you can see the carbon nanotube and vertipole, and you can see this is quite interesting. I can tell you the future slides. How to build the things in the nanoscale. You can see here, this is a macro scale missions. You can see here, this is the conventional missions, big size made by that bulk material. But after technology development, we used some microelectronic devices. The size is very small when compared to that bulk material. After technology development, now we can develop the nanotechnology product. Bottom of cell possible. This is a portable device we can carry anywhere else. This is the technology development. An introduction about the nanoscience and nanotechnology. It is a new breath of material science. Because inactive for different technology application in bulk material, but active for nanostructure material. Because the reason is it is exhibit extraordinary physical and chemical properties at nanoscale. The concept is developed by Richard Feynman during his lecture. There is a plenty of room at the bottom in the year of 1959. That means many invisible things surrounding with us. The normal human eyes, we cannot see that, but we can see with the help of scanning electron microscope and transmission electron microscope at the nanoscale. So it is also to manipulating and control the individual atoms and the molecules. So interest in developing of nanomaterial because their extraordinary properties. The term of nanotechnology was used first by the Japanese scientist Norio Taniguchi in the year of 1974. The concept on production of technology that creates objects and future on order of a nanometer scale. You can see this is what is a nanoscience. Nanoscience is the study of phenomena and the manipulation of matter at atomic, molecular, and macromolecular scale, but the properties differ significantly from those at a large scale. And nanotechnology, the development of nanoscience is called nanotechnology, the science of manipulating atoms and molecules to make new materials and devices. The nanotechnology word is interdisciplinary. It is connecting the science and engineering people. The size occurs in the range of 1 to 100 nanometer. 1 nanometer is 10 to the power of minus 9 meter. That means about 3 atoms of long. For a very good comparison, the human hair wide is 60 to 80,000 nanometer. You can see that 10 image, you can see that the range of wide is 60 to 80,000 nanometers. A nanostructure material. Nanostructure material, you can see here, are those with at least one dimension falling in nanometer scale and include the nanoparticles like quantum dots when exhibiting the quantum effects, nanorods and nanowires, thin film, and bulk material made up of nanoscale building blocks or consisting of nanoscale structure. How the nanostructure material has developed? In the year of 2000, the nanostructure material developed in aerosols and colloids, and also many products developed with nanostructures, such as coating, nanoparticle reinforced composite, nanostructure metals, polymers, and ceramics. So we can call it as that is the first passive nanostructures. In the year of 2005, nanostructure material played a vital role in 2 areas. One is electronic and another one is medical. The nanostructure material are developed in bioactive, health effects such as targeted drugs and bio devices. And second, the physical chemical active such as 3D transistor, amplifiers, actuators, and adaptive structures. And 2010, the nanostructure materials developed in 3-dimensional networking and new architectures, robotics. We can call it as this is a third system of nanosystem. And now 2015 to 20, we can design by molecular devices by controlling the size of molecule and like atomic design. So we can call it as this is a 4th molecular nanosystem. Categories of nanostructure material. The material categorized with, you can see this is quite interesting. There are 3 categories. The synthesized material with new properties by means of controlled manipulation of their nanostructure on atomic level has become emerging interdisciplinary, the field of solid state physics, chemistry, biology, and material science. The material involved may be divided into the following 3 categories. The first category is a quantum dot, the core shell. You can see that nanometer sized particle, thin wires or thin film. And second category is a diamond, the thin surface region of bulk material like PVD, CVD ion implantation and laser beam of treatments. And third category is a nanometer sized building blocks, mostly crystallites. This is very quite interesting. What makes technology at the nano scale different from technology at the macro scale? You can easily understand. I can provide a very good example. You can see here, there are two cubes. One is a big size of cube and another one is a small size of cube. The big size of cube, we assume that this is a bulk material, and small size of cube is, we assume that is a nano. The cubes are all sides are equal. You can see here, the each side is a 10 centimeter, right? So what is the surface area of the cube? The surface area of the cube is 6a squared. You can substitute a is a 10. So surface area 600 centimeters squared and volume is a cube. So a is a 10. Volume is 1000 centimeter cube. What about that volume to surface area ratio for big size of cube or bulk cube? That is 0.6 to 1. And you can see that small cube or nano cube, the side is 2 centimeter, the surface area is 24 centimeters squared, and volume is 8 centimeter cube. You can see here which one is high volume to surface area ratio. You can easily understand that small size of cube. That means nanostructured material have volume to surface area ratio is more when compared to the bulk material. So that the nanostructured material have extraordinary properties when compared to the bulk material. And another example, you can see here, this is a bulk micro scale material. You can see here the micro material do not cover that whole surface area, but you can see here nanostructured material cover that surface area. So the more surface area higher than that of this micro scale material. That is the advantage of nanostructured material. This is quite interesting. There are two scales. One is a natural scale, it's a God made. This is a man made. You can see here, hand size is 5 millimeter. The typical size man made it, head of the pin, 1 to 2 mm. Like this, dust mite size is 200 micrometer. The typical size we made it that some microelectronic components in the micro scale. Like this, the DNA 2 to 12 nanometer diameter. Like this, we made it the carbon tube and buckyball. That's a similar kind of scale. And next is very, very important, the quantum size effect. You can see here, generally the material classified with energy band gap. You can see the energy band gap consists of two band, valency band and conduction band. You can see here that big size, that means bulk material. You can see here that band gap is very small. When you're reducing the size, you can see here this band gap is. When you're reducing the size in the smaller scale, the band gap values, you can see that increase and emitting the different colors. So tune the electronic and optical properties when you're reducing the size. You can see here, this is a bulk material. When you emitting the red color, when you're reducing the same similar material, reduce the size in small scale, you can see here the band gap values increased and emitting that green light. And again, we can reduce the size in the small. You can see that the band gap values are again increased and emitting this blue color. That is called as quantum size effect. You can see nanotechnology is not a new. Many examples are there. Gold nanoparticle is reflected as a red color, but bulk gold is reflected in yellow color. Some old paint, you can see here the concept is existing in the 5th century. The colors in stained glass windows in many palace due to the presence of nanoparticle of silver and gold. When the sunlight is falling on it, they're changing the color. That is a quantum size effect. You can see here this similar. You can see the gold nanoparticle in the glass. The size is 25 nanometer, but reflected color you can see here red. Again, the size is increased 50 nanometer. Reflected color is green. And then again, the size increased, the reflecting color is yellow, like this, the silver nanoparticle. This is a similar example, the presence of nanoparticle of gold and silver. You can see the transmitted light is in the different color. Yeah. Another important things, the nanotechnology is already existing in that nature. You can see that many example belonging to natural world, the remarkable property due to inherent nanostructure. You can see here, this is a lotus leaf. The water droplet do not stick on the lotus leaf because it is a super hydrophobic nature and coatings on the lotus leaf. We can assume that this is a self-cleaning process in the lotus leaf. And also the butterfly changing the color. This is the quantum size effect. And then, you know, you can see the spider's silk made up of nanometer wire, the protein crystal. You can see this thickness very, very small scale in order of nanometer. So many things, insects and lizards are able to stick on the wall. You can see here, stick on the wall because of this nanostructure on this feet. Okay, what are the types of nanomaterial? The nanomaterial can be classified. There are 4 categories. One is zero dimensional. That means length, breadth, and height are confined at the single point. So we assume that that is called as a nano dot or quantum dot. And one dimensional, it has only one parameter, either length or breadth or height, the very thin surface coating. That is called as one dimensional. The example is carbon nanochips. The 2 dimensional, it has only length and breadth. For example, nanowire and nanochips. And 3 dimensional, it has all parameters of length, breadth, and height. For example, is nanoparticle or graphite. You can see that the classification of nanostructure material with the help of this FESM image, the fluorine. The FESM image, you can see that here, zero dimensional image, we can easily, we can see that. But normal human eyes we cannot see, but we can see with the help of this FESM. And like this, the nano red shape, one dimensional, you can see here one dimensional nanostructures, and 2 dimensional is a nano sheet surface morphology, we can observe that, and 3 dimensional is a nanoflower structure. And what about the property of nanostructure material? You can see this is a bulk material. When reducing the size in the smaller scale, like a nano scale, in order of 1 to nanometer, what about the properties are increased? You can see the surface area is increased, antibacterial properties are increased, oddness properties increased, and electron band gap, electric properties, and mechanical properties. You can see the catalytic properties, high surface to volume ratio, electrical properties increase the electrical conductivity, and improve the oddness of the metals and alloy, and optical property, spectral shifts of optical absorption and fluorescence. And magnetic also increase the magnetic coercivity, supermagnetic behavior. Effects of controlling the properties of nanostructure material. There are 4 effects. One is the size effect, which means modifying the mechanical and optical properties due to the changing the size, and changing the dimensionality, 1 dimensional or 2 dimensional with respect of this phenomena, and changing the atomic structure. The crystallites changes the atomic structure relative to the perfect crystal. And then the 4th one is alloying of components. That means the nanostructure material have different chemical composition. You can see there's a size dependent of properties. What about that properties, how changing with respect of size? You can see the chemical properties, reactivity and catalysis, and thermal properties, melting temperatures decreases, and mechanical properties, addition and capillary forces, and optical properties, absorption and scattering of light, electrical properties, the tunneling current, and magnetic properties, the supermagnetic effect. You can see this very quite interesting, the thermal property of nanostructure material. When you reduce the size in the smaller scale, you can see the surface energies increases, so that the melting point is decreases. Because the reason is the surface atoms require less energy to move because they are in contact with the fewer atoms of the substance. I can provide it here that good example. You can see the cadmium selenide. It is heated at 700 Kelvin for nanostructure material, but bulk material we need for the higher temperature. And also this is quite interesting. You can see the nanoscale optical properties. The bulk gold appear in the yellow color. When you're reducing the size in the small scale, you can see the gold appear in the red color. The reason is the particles are so small that electrons are not free to move about is the bulk gold. Because this movement is restricted, the particles react differently with the light. What about the properties of nanoparticle? The size of the particle has significant influence on its physical and chemical properties, and also its extraordinary properties, physical and chemical properties in the nanoparticle. There are 3 reasons. The first reason, size of the nanoparticle is comparable to Bohr radius of the exciton. The Bohr radius of the exciton, that means, the distance between the proton and electron in a hydrogen atom, it is comparable with particle size. That is called as a quantum confinement. You can see that another one. You can see this is a graphene and carbon nanotube. These layer structures have unusual properties because the reason is the particle sizes decreases, the net internal cohesive force increases. As a consequence, the surface energy that depends on the internal cohesive force. should increases with decreasing the particle size. When you're reducing the particle size, that increasing the surface energy. And third, this is also quite interesting, the formation of dangling bond. That means missing of one or two adjacent or unsaturation existing in the coordination. That is called as a dangling bond. This dangling bond, the surface atoms are suffering due to the unsaturation in the coordination. The increasing the number of surface atoms result increasing the dangling bond. So the greater number of dangling bonds, the higher surface energy increase. Yeah, this is quite interesting. You can see how changing the property with respect of the size. This is bulk material. You can see the bulk material in different shapes. And reducing that nano scale, you can get that say a particular shape like cubical, spherical, hexagonal, whatever you need, you can make it. And optical properties, highly transparent. When you're reducing the size, you can use the quantum dot. And electronic band gap, you can see here the bulk material. For example, metal and metal oxide in bulk form, the conductive there is no band gap. The band gap is very small. But when you're reducing the size, the band gap is increased. It's comparable with semiconductor material. So that nowadays, the technology development, especially electronic devices made up of metal and metal oxide, the reason is increasing that band gap value. You can magnetic properties also, you can see here this bulk material, but the super paramagnetism properties occurred in that nanostructure material. These are mechanical properties of this bulk material. When you are reducing the size, you can make it as a diamond nano material like this, glass or diamond material. Okay, how to synthesize nanostructure material? What are the techniques? There are two techniques. One is a top-down process. Another one is a bottom-up process. The top-down process is a big size. That means bulk materials are divided into the small size. That means cut into the small size in the order of 1 to 100 nanometer. That is called as top-down process. And bottom-up process is a building of atoms or molecules in atom by atom or molecule by molecule or cluster by cluster to form the nanostructure in the order of 1 to 100 nanometer. That is called as bottom-up process. You can see here nanostructure material fabricated by two ways. One is a bottom-up process. What are the techniques are used? You can see that atomic and molecular condensation and vapor deposition, then sol gel process, spray pyrolysis, chemical and electrochemical deposition, aerosol process, bioreduction. And top-down process is the coating, sputtering, chemical etching, thermal laser ablation, mechanical ball sling, and explosion process. So these are all techniques are used to prepare this nanostructure material by top-down and as well as bottom-up process. You can see the top-down process. The top-down process is very quite interesting. High energy ball milling. You can see here, this is a container. Container contains that metal ball. If you want to reduce the size, any kind of material, you can put it to the container, and then you can apply the electric field. So this metal ball crush this material. It can reduce the size in the order of 1 to 100 nanometer. It is a ball milling process where a powder mix placed in a ball mill is subjected to high energy collision from the balls. So we can reduce the size in the order of 1 to 100 nanometer. So you can controlling the size also with the help of this technique. This technique was developed by Benjamin and his co-work in the year of 1960. This method to produce uniform dispersion of oxide particles like Al2O3, Y2O3, THO2 in nickel-based superalloys that could not made by more conventional powder metal imager. All engineering department, they have this ball milling technique. They can use to reduce the size of materials with the help of this high energy ball milling technique. And next is the bottom-up process. I am going to explain a few methods how we can prepare the nanostructure material. You can see here, this is a co-precipitation chemical method. Chemical precipitation method is one of the most simple and convenient method. We can controlling the concentration of the precursors and temperature, pH of the solution, and reaction time. You can see here, I mentioned here cobalt ferrite nanoparticle prepared by this co-precipitation method. So there are two precursors. One is a cobalt nitrate and iron nitrate mixed together. with suitable solvent and mixed together with the help of magnetic stirrer. The solutions precursor are stirred with vigorously at 800 degrees Celsius. After getting the homogeneous solution, then we added that capping agent, sodium hydroxide. What is the role of the capping agent? The capping agent is controlling the growth of agglomeration. So it is controlling the size. After adding that capping agent, you can see that the solution became a colloidal, and then you can heat up the colloidal solution with the help of the hot air furnace. After heating and washing, and you can get the final product. This is cobalt iron oxide nanoparticle. What is the advantage of this technique? Very simple and rapid preparation, easy to control the particle size and combustion. It has operated at the low temperature and energy efficient. The disadvantage is time consuming, not applicable to uncharged spaces, and then batch to batch reproducibility problem. This is a disadvantage. And then another method is hydrothermal synthesis. Generally, the hydrothermal synthesis prepared because of its potential advantage. It is operated, the cost effective, and also it is a single step method, highly crystalline, highly healed. It is, hydrothermal method. It is look like a pressure cooker. This is a Teflon lined autoclave. The precursors, you can the solution taken in that Teflon lined autoclave and kept in that temperature. You can changing the concentration of precursors. You can get the different size and shape, and also you can also changing that temperature. So the changing the temperature with you can tune the size and shape also. So by this method, many graphene nanocomposite and binary compounds preferred by this hydrothermal method with highly crystalline nature of this sample nanostructure material. Another method is a sol gel technique. The sol gel technique, you can see here the precursors are dissolved with any gel medium. You can see this is a gel sol gel. After the gel medium, you can go for that try as a powder in the calcination. You can get powder form. If you want to prepare as a film, you can use the solution. This is a colloidal solution, and by you can immerse that substrate like glass or any aluminum foil with the heating. Then you can prepare the film by dip coating method. This is a sol gel dip coating method, and as well as you can prepare that thin film by using spin coating. So the sol gel method, you can prepare both powder and as well as film in this technique. Nanostructure thin film prepared by this sol gel dip coating method. And next is the microwave synthesis method. This technique also useful for synthesis of high quality nanomaterial. We prepared tin oxide nanosphere decorated on the graphene sheet. So we use the graphene oxide ultrasonicated for 2 hours, and then we added citric acid and then tin chloride hydrate. After mixing the solution, we can with the help of magnetic stirrer. After getting the homogeneous solutions, we just kept in that microwave oven. You can see by changing the precursor concentration, the solvent, and also instrumental parameters like micro power, pressure, and temperature. You can change, you can get different size and morphology. So many nanocomposite material prepared by this method, binary ternary component also prepared by microwave method. So it's very simplest and easy technique. And what are the type of nanomaterials? Type of nanostructure materials, there are 9: nanopouch, nanocrystal, nanobelt, nanofiber, nanoparticle, nanotube and nanorod, nanowire, quantum dot, and nanocomposite. You can see the nanopouch. This nanopouch concept reported in 2002. A nanomaterial has hollow interior and porous walls containing the metallic nanoparticle inside. You can see here, this is a metallic nanoparticle, Ag or Au. The size range between the 1 to 10 to 50 nanometer. What are the application? When you're preparing this kind of nanocatch, you can see the SEM image. This is a metallic nanoparticle. You can see here in the porous hollow interior, you can see here this metallic nanoparticle. So this kind of material could be very much useful for drug delivery application. And next is a nanocrystal. Nanocrystal is either single or multi-phase crystalline with a grain size less than 100 nanometer. It can be used for different applications like memory devices, solar cells, solid-state display, photodetectors, field effect transistor. Many applications can be used for that nanocrystal materials. And next is the nanobelt. Nanobelt is thin and you can see it is quite interesting. Is a thin and rectangular structure. Typically size is 30 to 300 nanometer. Nanobelt with a rectangular cross-sectional and well-defined crystalline facet, enable to attain the unique optical confinement, microcavity, catalysis, and piezoelectric effect. So where it can be used, this kind of nanobelt can be used for field effect transistor, nanometer-sized ultra-sensitive gas, and biosensor, resonator, cantilevers. So many applications. And nanofiber. You can see that SEM image of nanofiber. This is nanofiber structure, the 2D structure, the diameter less than 100 nanometer. It can be used for potential application in different areas: water filtration system, surgical implants, biosensor, drug delivery system, electronic device, tissue engineering. And then this is a nanoparticle. The nanoparticle initiate with the dimension is 1 billionth of meter, that is 1 10 to the power minus 9 meter. It is known as a nanoparticle. Nanoparticle, potential application in different areas like biomedical devices, biosensor, tissue engineering, drug delivery, bioactivators, bioimaging devices, and then electronics and optoelectronic devices, food industry, construction industry. So many applications used for nanoparticles. And then this also quite interesting, the nanotube and nanorod. Nanotube is a microscopic tube whose diameter is measured in the nanometer scale, less than under nanometer. Nanotube is mostly hollow, but nanorod is a solid structure with the aspect ratio is 3:5. The dimension from nanorod is 1 to under nanometer. It can be used for many potential applications like supercapacitors, actuators, and electromagnetic shields. And nanowire. Nanowire is a smart 1D nanostructure material with the dimension the order of 10 to the power of minus 9 meter. It can be used for fabrication of p-n junctions, transistors, solar cells, and sensor. This is a quantum dot. Quantum dot is a nanocrystal of semiconductor material. You can see the quantum dot can contains a few under to 10,000 atoms within the quantum dot volume with the diameter of 10 to 50 atoms. You can see the quantum dot concept. It can be used for many optoelectronic device applications because tuned that optical and electronic properties. They can be externally applied to LEDs, light emitting diodes, lasers, biomarkers, biosensor devices, and biomedical imaging. This is the nanowire sensor. It can be used for detect the cancer. Nanowire detect the biomarkers of cancer. A nanocomposite. Two compounds mixed together to form the nanocomposite. It is a multi-phase material. One compound of one phase, another compound of other phase. So we can call it as a multi-phase of the material, where at least one constituent phase has one dimension less than under nanometer. The promise of nanocomposite lies in the multifunctionally the possibility of realizing unique combination of properties, and it can be used for different application of nanocomposite like microelectronic industry, aerospace, electronic packaging, and catalysis. I'm going to give some results about on magnesium oxide and zinc oxide nanostructure material. Magnesium oxide is one of the most fascinating and promising material with remarkable electronic, optical, magnetic, thermodynamic, mechanical, and electronic properties in this metal oxide family. So I'm going to present some results. Effect of synthesized temperature, optical, and electrical properties of nanostructures. You can see here this XRD pattern of MgO nanostructures at different temperatures. The XRD pattern of A is 100 degrees Celsius, and B is 300, and C is 600 degrees Celsius. You can see the plane indexed by 11, 200, 220, and 331. This plane corresponding to the cubic structure of this magnesium oxide. And also from this XRD, we can confirm that whether material has a crystalline or polycrystalline. You can see here the peaks, well-known peak, we observe that. So the MgO have that crystalline structure. And also we can calculate the grain size of this MgO nanostructure. The grain size calculated for 100 degrees Celsius is 9 nanometer, and 300 degrees Celsius is 11 nanometer, and 600 degrees Celsius is 50 nanometer. You can see here, when the synthesis temperature is increased, the grain size are also increased. The reason is that because of the agglomeration process induced from the material, and also electrostatic force involved. So due to the thermal energy, the grain size are increased. You can see here, 100 degrees Celsius, we can get 9 nanometer, but when we go for higher temperature, the grain size is 11. And also we can go for 600 degrees Celsius, the grain size is 15 nanometer. For young research scholars and students, you can try to understand what is a particle and grain. The particle means the group of grains is called as particle. You can see here many grains, there's many segments are there. Each segment is a grains. So each grain portions. From this X-ray diffraction analysis, we calculate the grain size, not particle size. The group of grains is called as only particle. You can see here this segment, we can calculate the grain size. So from the X-ray diffraction analysis, we calculated the grain size. There are two terminologies. One is the crystalline size and grain size. The crystalline size is the smallest, most likely single crystalline in the powder form. This is the crystalline size. And grain size is either single crystalline or polycrystalline material, and is present in either in the bulk or thin film form. Particle size we can calculate it with the help of transmission electron microscope. So there are two characterization techniques like X-ray diffraction analysis and scanning electron microscope are used to find the grain size of this nanostructured material. But particle size we can calculate it with help of this TEM, transmission electron microscope. And then this also quite interesting. You can see the surface morphology, how changing with respect of the synthesized temperature. You can see here 100 degrees Celsius, how the surface morphology of MgO. You can see here highly dense. Why here the highly agglomerated? The grains are highly agglomerated. That means surface energies are more. So surface energies are more, that means agglomerations are high. You can see here the 100 degrees Celsius, we observe that spherical shape morphology. When increasing the temperature, the synthesized temperature is 300 degrees Celsius, you can see the surface morphology is sheet-like morphology. You can see here, this is the sheet-like morphology structure, but agglomeration is very less. That means surface energy is less at 300 degrees Celsius. Again, we can go for 600 degrees Celsius. You can see the surface morphology needle shape. So you can changing the temperature, the synthesized temperature, you can vary, you can observe the different morphologies. And FTIR, what are the functional group? What are the metal functional group present in that compound? We can observe from that FTIR analysis. You can see that from this FTIR analysis, we can confirm that the stitching bending vibration modes of magnesium to oxygen occur in that range 870 centimeter and as well as 517 centimeter. The peak appeared to 613 also, corresponding peak of this MgO. This is another quite interesting of optical properties of MgO, magnesium oxide nanostructure. You can see UV absorption of different temperature. Absorption edge shows that 250 nanometer for 100 degrees Celsius and 265 for 300 degrees Celsius and 280 for nanometer for 600 degrees Celsius. You can see why it is, the broadband peak observed at 600 degrees Celsius, because that is MgO is a nano needles synthesized at 600 degrees Celsius, and also it is possess the quantum confinement. And then we calculate that band gap energy for MgO nanostructure by using the tau plot. You can see here from that tau plot, the band gap energy were calculated to be 4.89 electron volt for 100 degrees Celsius. And synthesized temperature at 300 degrees Celsius, we calculate the band gap is 4.84 electron volt. And 600 degrees Celsius, 4.43 electron volt. You can see here when synthesized temperatures are increased, but here the band gap values are decreased. The reason is the band gap should be associated with increased grain size, decreased carrier concentration, tensile stress on the oxygen vacancies. leading to decrease the carrier concentration in the conduction band. And then we performed that electrical property of magnesium oxide nanostructure. We did dielectric constant, dielectric loss, AC conductivity, and cold flat. You can see this is very good, quite interesting of dielectric property of MgO nanostructure. Dielectric constant decreases with increasing the frequency, and dielectric constant increases with increasing the temperature. You can see here dielectric constant increases with increase the temperature. And also high dielectric constant at lower frequency and low dielectric constant at higher frequencies. The similar behavior we observe that dielectric loss. You can see here dielectric loss also decreases with increasing the frequency, and also dielectric loss increasing with the increasing temperature. Though dielectric loss occur at that higher frequency, you can see here this low dielectric loss occur at higher frequency. So this confirm that the material have that there is no defect. And then for figure C, you can see the AC conductivity of this MgO nanostructure. AC conductivity increases with increasing the frequency, and as well as AC conductivity increase with increase the temperature. And this one is a cold flat. The complex impedance spectra contains a single semi-arcal at you can see all temperature like 100, 300, and 600. Because the reason is MgO nanostructure, which are due to the contribution of grade resistance. The next material is zinc oxide nanostructure. You can see that UV absorption spectrum of zinc oxide nanostructure. It is observed, the UV bond observed 350 nanometer, and this is a FTS spectrum of zinc oxide nanoparticle. We can confirm that zinc and oxygen bonding it is occurred in 500 to 800 centimeters in this one. This is the XRD pattern of zinc oxide material. You can see the well-known peak confirm that material have the crystalline nature, that 110002 obtained indexed by JCDS software, Giant Commission Powder Diffraction System. So it is very good. This plane corresponding to the external structure of this zinc oxide nanoparticle. Using the Scherer equation, we can calculate the crystalline size. It is found to be 70 nanometer. Yeah, you can see the surface morphology of zinc oxide nanostructure, the different magnification of same image. You can see that spherical shaped grains are located and highly agglomerated, the different magnification. And also we can confirm that transmission electron microscope, you can see that spherical shape of grains particle, we can see that here. So from this term, we can calculate the particle size. And also the SID pattern confirm that very good agreement with this excentric plane. You can see the concentric plane, the concentric circle indicates that each plane of this excentric plane. And also we perform that electrical property of MgO. You can see here the dielectric constant, dielectric loss. You can see here different temperature with respect of frequency. Dielectric constant decreases with increasing frequency, dielectric constant increases with increasing the temperature. This graph shows that dielectric constant with respect of temperature, but at different frequencies. So when increasing the temperature, the dipoles relatively acquire energy and become free, and so respond to the applied electric field. So therefore, the polarization increased with the dielectric constant also increase with the increased temperature. You can see here. And like this, a similar dielectric loss with respect of temperature at different frequencies, 1 kilohertz, 2 kilohertz, 3 kilohertz, and 4 kilohertz. The lower value of dielectric loss at higher frequency was due to the reduction of domain walls resonance and molecular alignment with the applied field. You see that here AC conductivity. AC conductivity of zinc oxide, you can see here AC conductivity increases with increasing the frequency, and as well as AC conductivity increasing with increasing temperature. Then you can see there are two graph here, ln sigma c with respect of 1000 by T temperature. This Arrhenius flat. From this flat, we can calculate that activation energy. You can see this AC conductivity Arrhenius flat from the activation energy can be calculated to be to 0.29 electron volt. Similarly, you can see this DC conductivity. The activation energy was calculated to be 0.32 electron volt. And then next is a metal oxide nanocomposite. The metal oxide nanostructure play a very important role in many areas: physics, chemistry, and material science. Metal oxide have now been used in many areas like catalysis, ceramics, fabrication of microelectronic circuit, piezoelectric devices, sensor, fuel cells, electro-optical, and electrochromic devices. So now I am going to discuss zinc oxide and magnesium oxide nanocomposite. This nanocomposite prepared by sol gel method. You can see here this preparation of nanocomposite. We started the reaction by taking tetrahydrate of zinc acetate and the magnesium acetate in the different ratio. One ratio is 1.0, 1.5. Another one is 1.5, that magnesium acetate. Both the precursors were dissolved individually in 50 ml of double distilled water, mixed thoroughly to form the homogeneous mixture. After that, we added 0.5 m acetic acid with the maintenance of temperature in the range of 50 to 60 degrees Celsius for 4 hours. After the period, we seen the formation of gel, after which on drying at room temperature, formed the white powder product, was subjected to drying at 90 degrees Celsius for 6 hours in the outer oven. Finally, the obtained product was further annealed at 500 degrees Celsius for 2 hours. We observed that two different ratios of the sample, namely MZ1 and MZ2. You can see this exact pattern of MgO ZN nanocomposite with the different ratios. The first one is MZ1 and another second one is MZ2. The different ratios prepared the nanocomposite. You can see that peak indexed by JCPD software. You can see the plane indexed by 11002, 101. The star indicates that the corresponding plane of zinc oxide is a oxide structure, and 200 and 311. That plane indicates that cubic phase of this magnesium oxide. So we confirm that the two compounds present here and also structure of this material we observed. One is a zinc oxide structure is oxide, and another one is a cubic phase of magnesium oxide. And then we calculate the crystal size. You can see the crystal size calculated from the two different ratios of this composite. You can see here the crystal size was found to be for MZ1 is like 2576 nanometer for MZ1 and 2143 nanometer for MZ2. You can see that when you're changing the concentration of this precursor or when changing the ratio, you can see that grain size also changed. You can see here 20.576 for MZ1 and 21.43 for MZ2. Yeah, this is very quite interesting. You can see that there is an image of different ratio of this nanocomposite. You can see that A and B, the first ratio of this composite we mentioned here, M is at 1. You can see that how the grains are located. You can see from this figure indicates that the formation of plaques which are highly agglomerated. It is like a mushroom-like spherical shaped morphology. You can see that A and B. And C and D, you can see here, this is a MZ2 nanocomposite, less agglomeration, you can see here, and also indicates the mixed morphology of nanoplaques and spherical shaped particles with less agglomeration. So from these slides, the larger grain is attributed to the agglomeration of smaller grains. Once again, it is evident from the FSM micrograph that there is a small difference in the shape and size of the particle for different composition. And then we performed that FKAR, the absorption band around 400 to 800 centimeter, confirms the metal oxygen system of vibration, like magnesium oxygen and zinc and oxygen. The broad band around 437 centimeter in one and 1,500 centimeter in one are attributed to the OS switching and bending vibrations which indicates the presence of water molecule on the surface of the nanocomposite. And then we performed that photoluminescence, the strong emission peak. You can see that graph, for 444 nanometer, the strong emission peak observed in all the different rays of this nanocomposite to the electronic band to the band transition. And also the broad blue emission band in the visible region is due to the excited transitional defect state. And then we perform that magnetic properties of this nanocomposite. This nanocomposite of two different ratios, the weak ferromagnetic behavior was observed, so which could be useful for spintronic devices. You can see the presence of exchange bias effect in zinc oxide MgO nanocomposite due to the uncompensated spins between the ferromagnetic and antiferromagnetic interface, significantly important in the magnetic data storage device and spin values. You can see we calculate that magnetic parameters like susceptibility, resonance, magnetic coercivity, and squareness ratio. We tabulated here. You can see this first ratio of the sample. You can see the small squareness value indicates that the synthesized nanocomposite are highly useful for core material, for transformer, and electromagnet application. Again, we performed that electrical properties of these two different ratios of the nanocomposite. You can see the figure, the variation of dielectric constant and the dielectric loss with different temperatures and different frequencies. The value of dielectric constant and dielectric loss are maximum at low frequency. You can see here to the applied field, and decreases continuously with the increasing the frequency. You can see here the frequencies increases, it decreases. Maintain a constant value at higher frequencies. Then the value of dielectric constant increases with increasing temperature, which due to the increase the mobility of ions. And AC conductivity also increases with the increasing the frequency and increase with the increasing temperature. This Arrhenius plot, we calculated activation energy of this different ratios of these nanocomposite. You can see here the different frequencies. We calculate that activation energy of different composites. M1 and M2, different ratios. 100 Hz, 1 kilohertz, 10 kilohertz, and 100 kilohertz. You can see here that first ratio of the sample is quite higher when compared to the M2. This is impedance analysis. From the figure, the impedance spectrum analysis shows that real and imaginary part. The real part of impedance is resistive, and the imaginary part of the impedance is reactive. You can see that from the graph, the real part of impedance resistive and imaginary part of the impedance decreases with increasing the frequency. And temperature, you can see the temperatures merged. You can see here the graph merged to single line at higher frequency. You can see that higher frequency, all the temperatures are merged to the single line. And then we perform the cold-cold flat. The cold-cold flat of complex impedance spectrum contains a single semicircle at low temperature for zinc oxide and magnesium oxide nanocomposite with different ratios due to the contribution of grain resistance. From the graph, the observation of small arc, you can see that small arc, the observation of small arc, a semicircle in the cold-cold graph at high temperature is due to the grain resistance. That means bulk and the grain resistance getting decreased for increase the temperature, so that the radius of the arc of the semicircle is reducing with that of increasing the temperature. You can see that temperature increased from 303 Kelvin to 573 Kelvin. At higher temperature, highest temperature of 573 Kelvin, the two semicircles are formed. The first semicircle of high frequency in the next plot is linked to the bulk, that's the grain effect, while the second semicircle is a low frequency region is due to the grain boundary effect. Yeah, this is also another quite interesting slide. We prepared cobalt oxide nanoparticle by hydrothermal method. You can see the SEM image of cobalt oxide nanoparticle. You can see that A image is a nanocube. When you changing the synthesized temperature, you can see different temperature of B and C and D, E. Nanoflower structure, nanowire structure for B, and again the temperature change, nanoflower, nanoplate, and nanobundle. So the temperature played a vital role to changing the surface morphology. if you are want to changing the surface morphology, you can change the temperature. So I conclude this, from this result, we performed that metal oxide and then metal oxide nanocomposite for the different applications. I mentioned a few results here. Next, I'm going to give some application of graphene, the general applications. Graphene was synthesized by two methods. One is a top-down and bottom-up method. Generally, the graphene was synthesized by chemical method at room temperature. The graphene is a honeycomb-like structure, sheets of carbon material with sp2 hybridized atom. You can see that why graphene structure material have unusual properties. The reason is surface area is high. You can see here the graphene sheet can cover the half of this football ground. That's a good example. And highest electrical conductivity, 10 to the power of 6 Siemens centimeter inverse 1. And also these graphene materials are strong mechanical properties. How much of strong the graphene? The graphene is the strongest material ever measured. 200 times stronger than structural steel. You can see that example. He would talk on the elephant balanced on the pencil. The pencil made up of this graphene to break through the sheet of the graphene. That much of thickness, the breaking strength of this graphene material is 42 Newton meter inverse 1, the excellent thermal conductivity. So the graphene can be used for potential application in many areas. You can see here graphene used in gas sensor. You can see here this is a graphene structures developed with the silicon oxide substrate. You can see this is a gas molecules. There are two electrodes that time, and another one is a gas molecule. So you can see here this is a gas molecule. This of course is another electrode. So graphene-based gas sensor have recently attracted intensive for mainly due to the atom thick two-dimensional structures and excellent properties of graphene sheets. Graphene is a unique and attractive sensing material for gas sensor. And this one is a graphene-based nanocomposite. This graphene-based material, it can be used for biosensor application. You can see here how the graphene material developed in that biosensor application. The transducer is a part of the sensor which converts chemical information to measurable signal. You can see here this is a gate dielectric and respirator molecules and different electrode. This is electrolyte and target that biomolecules. And this one is, you can see here, drain. This is a graphene-based nanomaterial. Could be useful for that biosensor application. And application using graphene polymer composite, it can be used for solar cell application. It is a titanium, indium tin oxide in the polymer-based solar cell. The graphene in the electrode becomes an organic inorganic hybrid material after it undergoes the coating, layering, reduction, and temperature annealing. So this is a potential application for this solar cells. And also nanocomposite, you can be used for drug delivery applications, biomedical applications like tissue engineering, drug delivery, cellular therapies. Because the reason is unique interaction between the polymer and nanoparticles. A range of property of combination can be engineered to mimic native tissue, any structure and properties. And application of carbon nanotubes, you can see here the carbon nanotube based biosensor are recognized to be a next generation of building block for ultra sensitive and ultra fast biosensing system. Application of nanotubes. Nanotubes can be used for potential application in lithium-ion batteries. You can see the carbon nanotubes due to the unique structural, mechanical, and electrical properties. Application using the nanofibers. Nanofibers have many possible technological and commercial applications. They are used in tissue engineering, drug delivery, cancer diagnosis, lithium-ion battery, and optical sensor and air filtrations. You can see here this is a nanofiber is acted as a drug loader and then injected with the blood vessels, and it's killed the cancer cells. application using the wires, nanowires using the biological, chemical, and gas sensor. There's many applications. Application of metal oxide. So metal oxide, it can be used for different areas like transistor, sensors, lithium-ion batteries, energy storage, solar cells, catalytic and photocatalytic process, non-volatile memory devices, tunneling devices, bioceramics, and antibacterial coatings. You can see here many materials developed with the help of this metal oxide, the gas sensor, humidity sensor, antibacterial coatings, microwave device, supercapacitor, lithium-ion batteries, high density recording system, solar cells, solar filters, transistors, VLSI applications, and organic LEDs, and optical lens, optical windows. So many products made up of with metal oxide nanoparticles developed. What are the some applications of nanotechnology? Nanotechnology, it is covered in like you can see here, mechanical engineering, robotics, biotechnology, transportation, defense, food and agriculture, medicine, aerospace, energy, environmental, advance of medical textiles, information technology. Why the nanotechnology products be preferred? The reason is the nano product is lighter, stronger, faster, smaller, and more durable. You can see there are over 800 products on the market that either have nanostructures or have been developed through nano process. Advancement of nanomaterial make lightweight material and also help to reduce the size of equipment developed. You can see here many products made up of nanostructure material like medicine, defense, and electronic products. This nanocore introduced by Tata is very low cost, affordable price with the nano size core. You can see some nanostructure materials are developed in that aerospace application because reduce the size. You can see that nano technology also offer scratch resistant surface coating. You can see glass is made up of nanostructure materials. And in electronics, you can see many electronic products. The electronics industry is getting smaller and faster all the time. The computer chips pictured above contain millions of transistors to run a variety of electronic devices, including the computers, digital cameras, memory sticks, and traffic lights. The LED lights found in traffic lights and display boards are the product of micro and nanoelectronic research. This is biomedical application. Medical and pharmaceutical products are important areas where the nanoscience is being used to create new methods, resources, and products. You can see here consumer applications. Many applications are developed. Electronics, improving the display screens and electronic devices, increasing the density of memory chips, reducing the size of transistor used in integrated circuits. Medicine also diagnostic, drug delivery, like iron and gold nanoparticle used in the cancer treatment, tissue engineering application. And space also, advancement of nanomaterial make lightweight solar cells. And food also, nanotechnology played the vital role. It can improve the food packaging. Nanomaterial can improve the health benefits that food delivers. You can see the nanotextile. Nanofiber makes the cloth, water and stain repellent. Textile with nanotechnology finish can be washed less frequently at low temperatures. Many products based on that nanotechnology, nano optics could allow for increasing the precision for repair and other type of laser eye surgery. Is nano optics. And the next is the nano computing technology. Nano computing technology, the next generation of computer chips. The microelectronics industry has been emphasizing miniaturization, whereby the circuits such as transistors, resistors, and capacitors are reduced in the size. By achieving the significant of reduction in the size, the microprocessor which contains this component can run much faster, thereby enabling the computations at greater speeds. So nanotechnologies played the vital role in different areas, chemical sensor and solar cells. I mentioned here that slides for medical applications. There are two kind of drug delivery. One is a untargeted drug delivery. You can see here the drug. It can be injected to the generally. Okay, so it kills the 6 cells. But here, this is a nanotube acted as a carrier and drug loaded in the nanotube and injected where you want inject the drug. And it is targeting the 6 cells and it kills the 6 cells. So you can get we can get relief immediately. So these are advancement of targeted drug delivery system. And also you can see nanostructured materials acted as a both. One is a drug and as well as a carrier. Some drug is loaded in the nanoparticle. It is injected to the human body. It can you can see that from this image. You can see this is a low systematic toxicity, this high systematic toxicity. So drugs are able to reach the site of action more effectively, and it's killed the 6 cells. This advancement of material can target various cells, like cancer cells, any kind of cells. You can see the drugs modified with a different molecular shape and chemical properties can be synthesized like this. Different properties result in the greater possibilities. As I told you that you can changing the size or shape, you can get the different properties. What is the advantage of this nanostructured material in biomedical application? Because the reason is, the first reason is the size is very small, eye surface to volume ratio, and then one or more therapeutic drugs can be attached because size is very small, and helps to avoid the fluctuation of drug by using the time to release. You can see these carbon nanochips carrier have molecule to standard contain the antibodies and link to the system to the cancer cells. You can see that cancer cell by pH and biological markers. And also the carbon nanotube drugs inside the nanotube can be released in the presence of RF frequencies. The metal nanotubes also heat in the presence of radio frequency waves and burn the cancer cells. This also nanodiamonds release a drug into the tumor cells and result highly effective the treatment. So many potential application of nano structured material. So this is a overview of nanostructured material. For it is covered that energy, environment, then drug delivery, that means medical. Some nanostructured material is used to develop the solution of problem in the water quality. It helps the removal of industrial wastes from the water. Nanoparticle can be used for convert the contaminating chemical through the chemical reaction to make it harmless. And chemical sensor also, various type of detecting elements such as the carbon nanotube, zinc oxide nanowires can be used in nanotechnology based sensor. Nano batteries, the rechargeable batteries with a higher rate of recharging using nanostructured materials could be helpful for the battery disposable problem. And nanotechnology is used to reduce the cost of catalysis using the fuel cells. So many applications, many areas. Before conclude my presentation, just I want to give that another information. Our center launched 2 journals. One is a Malaysian Nano and International Journals. If you want to publish your paper, have any short notes or original research paper or review article, letters, or any short communication, you can submit to this journal. We can publish your paper very short time period. And also another journal is Malaysian Catalysis and International Journal. So if you want to publish your paper in this journal also, you can submit to our journal. You can check this information from our center website. We provided all the information in the website. So you can submit your paper, you can get quick publication. And also another information, our center going to organize the first Malaysian International Conference on nanotechnology and catalysis on 1st, 3rd September in Langkawi. You can see that information provided in that our center website, different areas. You can send, you can register your participation, and as well as you can submit the abstract. If you want to publish your paper in IAS and external, we can provide it. We can support for publication also in different journals. This is another journal of recent Journal of Material Chemistry. This is one of my collaborators as editor-in-chief, and I am one of the editor board member. So if you want to publish your paper in that journal also, you can send it to us. I'm International Journal of Multifunctional Material and Photoscience. So these are my collaborators. Thank you for your patience and
Okay, thank you very much for Dr. Suresh for giving us the informative and interesting topics, especially for in catalyst and nanocatalyst. Okay, Dr. Suresh, I have collected some questions from our participants. Maybe you can see here. We have maybe in 7 questions for Dr. Suresh. The first question, okay, you can answer one by one maybe, or if the question is same, maybe you can answer it generally. The first question from Mr. Yudhis Aziz from IPP. What is advantage using Sol-Jet method for ZNO and NGO nanocomposite than other method?
we tried with Sol-Jet method. They can go for hydrothermal synthesis also. We can use to prepare this composite, but I didn't try photo degradation, photocatalytic studies for this composite, because our aim looking for the electronic device application, optoelectronic device application. So we perform that electrical property and the magnetic properties. Maybe we can try. My students are working towards the photocatalytic activity of this composite. Can you hear me?
Oh, yes, I can hear you. Okay.
Yeah.
Yes, Dr. Aziz, maybe you can have feedback for Dr. Suresh.
Yeah, second question. Yeah. Second question, what is it? Nano size is different compared to the original size. Can you give the example? Yeah. You can see that different compared to the original size. Can you give the example? If there are any research in battery nano size? As I mentioned that many slides for that, how changing with respect of properties. When you reduce in the size, you can get different properties. As I mentioned that, all electronic devices made up of semiconductor material, we cannot use for metal and metal oxide, bulk material. But when you're reducing the size, metal and metal oxide increase the band gap value is comparable with this semiconducting range. So now many devices developed by, as I mentioned in the slides, metal oxide and metal nanoparticle. How we can differ the particle size and grain size, the nanoparticle from thin film. As I mentioned the slides, I can give a very good example. The group of grains is called particle. The group of particles called atom. Group of atoms called molecule. From this grain size, we can confirm that only from X-ray diffraction and the scanning electron microscope. Particle size we can calculate it from transmission electron microscope. Do you have any metal sulfide? Yeah, metal sulfide also you can change the similar kind of behavior of metal oxide. You can reduce the size, you can changing the properties like surface morphology and whatever chemical, electrical, and magnetic and mechanical properties.
Okay, maybe you notice from the Suganya Palani.
Yeah. What she mentioned that do you have any idea about that metal sulfide? Yes, we done that similar property for metal sulfide, zinc sulfide and cadmium sulfide, similar properties like structural, optical, surface morphology, electrical properties. But oxide material, it could be more convenient for photodegradation application. But metal sulfide nanoparticle, it could be useful for electrical and optical tune the band gap, and tune the electrical property also. So we did zinc sulfide, nickel sulfide, so many metal sulfide nanoparticle prepared by different methods like chemical, sol gel. So we studied that electrical properties and optical properties. So maybe she can try.
Okay. Maybe we have three last question, Dr. Suresh, from Dr. Hasano from American International University, Bangladesh, and Septian.
The same questions. They mentioned photocatalytic application. Maybe already many people are working on the nanocomposite for photocatalytic application, but this problem is we didn't try for the photocatalytic application, but one of my students is working on it, this composite for the photocatalytic application, but I didn't try for the graphene material for photocatalytic applications.
Okay. Maybe for the next question, Dr. Suresh from Septian.
The same things, how to avoid the agglomeration process. How to avoid the agglomeration process, as I mentioned the slides, we have to very important synthesis parameters. That means the precursors ratio and temperature and pH value. You can changing that different ratio of the precursors, controlling the pH value, changing the pH value. You can controlling the size and shape. Any kind of method, you can use this parameter. You can avoid that agglomeration process.
Okay, Dr. Suresh, I have some problem with Mr. Yuda, but I have tried to make a nanoparticle with top-down method.
Yes.
Using the ball milling, but I have some problem that the produced material have not homogeneous.
Yes. This is a problem for top-down process. In ball milling technique, the purity form and crystallinity nature is a big problem. But when you're using that bottom-up process, can you hear me? Hello, can you hear me?
Yes, I can hear you.
Yeah. So when you go for that bottom-up process, you can easily controlling the size and shape. As I told you, you can changing that any parameters like ratio of the precursors or pH value or temperature, synthesis temperature, you can controlling the size. But in ball milling technique, you can only controlling that voltage, right? The electrical power, and then the ratio of the precursors.
Okay.
Challenging, yeah.
Okay, thank you. Okay, maybe in the last question is in this section, Doctor, from the Muhammad Shahjahan from Chittagong University.
Yes, watt-based graphene transport for solar cells, right? Possibility. Graphene nanocomposite. So graphene with metal oxide or metal nanocomposite is a potential application for this solar cell application.
Okay, I think it's enough for all, and thank you very much for Dr. Suresh has present the interesting topic. I note from
once again I thank the organizer, host and co-host, and Professor Fatima giving the invitation to share my experience. I hope everyone understands the fundamental concept of nanoscience and nanotechnology.
Okay. I think it's enough from me, and but before I close the section, maybe I can conclude the section. And I note that the characteristic of material is major important for application in energy and environment. Okay, I'm sorry for all my mistake, and because our time is limited, I'm
no problem.
Return back to Professor Fatima.
Okay, thank you very much, Mr. Ganjar Fadilah, for a very nice moderating the session. Also to all speakers, Professor Rui Andong from National Tsinghua University, as well as to Dr. Suresh Sagadivan from Nanotech, Malaysia. As a token appreciation for your contribution, so we will deliver the certificate to Professor Rui Andong for today's event. Also to Dr. Suresh Sagadivan for
Thank you.
your thank you, welcome. Very
Thank
nice
you.
presentation, Prof. And Dr. Suresh, because
Thank you. Thank you. Thank you.
you present some little bit about the development of 3D carbon, which is very interesting for myself, because I think that it will be the benefit for us in Asian countries, because there are so many biomass source as the functional material for some application. Yeah, also the interesting talk from Dr. Suresh regarding to how to synthesis this nano material and nanoparticles for some application. Also, thank you very much for Mr. Ganjar Fadila for moderating this session for today. And for all participants, thank you again for your participation to this event. And because this event is a part of webinar series from chemistry department, so don't miss the next webinar conducted by our department. The next event will be on 3 September 2020. The webinar series on scientific writing with the speakers, Professor Rui Andong from National Tsinghua University, Associate Professor Dr. Muhammad Aziz from the University of Tokyo, Japan, and also Professor Dr. Eddie Heraldi from Universitas 11 Maret. And the next one will be on 12 September. This will be the webinar series in Advance in Essential Oil Research, collaboration between Chemistry Department, Universitas Islam Indonesia, and also the Institute System Biology in Biosis, University Kebangsaan Malaysia. So don't miss the events. And it is about to end of this session. So for all participants, you can download the certificate by following a link. I will give the link in the chat next. Okay. So that's all the agenda for today. Again, thank you very much and see you to the next webinar. Assalamualaikum warahmatullahi wabarakatuh. See you.
Thank you.
Waalaikumsalam warahmatullahi
Bye.
wabarakatuh.
Thank you, Chair Ismati.
Selamat siang.
Thank
Good
you.
day.
Assalamualaikum.
Thank you so
See you
much.
on
Waalaikumsalam.
September.
Bye.
Yeah.
Bye.
Yeah, bye.
Professor.
Yeah, Dr. Suresh, you also will have the next session to our next webinar.
Next webinar, yeah.
Yes, I will inform you later. Thank you.
Thank you, Fatima. Thank you, Prof.
Yeah.
Thank
See
you.
you.
Bye.
Bye.
See you. Bye.
See you.
Syairi Quran